to a tutorial on transforming graphs of functions. I'll just call it transforming graphs, and this is a topic at the higher level. We have seen very similar ideas actually at National 5 in the series of tutorials on trigonometry. There was one of the later tutorials in that group. We talked about transforming sine and cosine curves, sine and cosine functions, and this really is the same topic but more general, just thinking about any function f of x. So I'm just giving a single tutorial on this, but I will put a link in the description below the video to that National 5 video on transforming sine and cosine curves. So I'm going to use a particular function to illustrate these different transformations. But first, let me just list the transformations that we'll be thinking about. There are 6 of them in all. So if we're considering a general function y equals f of x and thinking of that as a graph plotted on the x and y axes, then the following are what transformations we need to consider. First of all, scaling in the y direction. So essentially multiplying the function by a constant. And if that constant is greater than 1, that will have the effect of expanding the function in the y direction. Also involving y would be adding a constant to the function. And this will have the effect, if that constant is positive, of shifting the graph upward in the y direction. If the constant is negative, it will shift the graph downward. I'll just use a different color for the x variable transformations. So just as we saw scaling in y, we can scale in x. But these ones involving the x variable tend to be a little counterintuitive. So if we scale the x variable by a constant, if that constant is greater than 1, because kx is actually the argument of the function, a value of k greater than 1 will have the effect actually of compressing the function in the x direction. Similarly, if we shift the x variable, so we're shifting the thing that goes into the function, shifting the input, it will have the counterintuitive effect on the graph. So if we have an additive constant added to x and then put that into the function, it will actually shift the graph to the left in a negative direction. Likewise, if we add to the input variable x a negative constant and have that as the input to the function, it will shift the graph in the positive direction. So these two transformations on x are counterintuitive, at least at first. If you get very used to them, they would become intuitive, but at first they would appear quite counterintuitive. And then the last two transformations, in a sense, are special cases of these scalings, but it's when k is negative. So if we write y equals negative f of x, this is actually a reflection of the graph about the x-axis. And similarly, if we write y equals a function of negative x, this is a reflection of the graph about the y-axis. So let's have a look at all of these with a particular example in mind. So I'm going to choose a parabola. I think you can tell by now that I'm quite fond of parabolas. Let me draw that parabola here in the lower left corner, and then we'll use the rest of the page to look at these various transformations. So we're going to do an example, and here we are. X and y, there's the origin, and the function I'm going to take is y equals -1 plus x squared. So when x is 0, y is -1. When x is plus or minus 1, y is 0. So we have these two roots. And this parabola, let me just sketch it first, will look like this. I jogged the pen there, I apologise. Try and smoothen that out a bit. So there's the function. I'm sorry for that little smudge there. And we have y equals -1 here, and this parabola cuts through the x-axis at x equals 1 and x equals -1. So there we are. I'll use this green pen to just erase that so that you don't think that we have some weird kind of branching function there. Right, so transformations on this parabola. For the sake of concreteness, let me always choose, for these examples, k equals 2, just for simplicity, and I will choose a shift of a equals 1. So you can see there's tons of choice here, the choice of the function and the choice of the scaling parameter and the choice of this shifting parameter. Right, so the first case we'll look at then is this scaling in y. So we're asking then about scaling this function y equals twice f of x. And how would that look? Right, well, it's not going to affect where this curve cuts through the x-axis, but it will affect the value of y at the origin. When x is 0, y will now be -2. But it's going to still cut through the x-axis at y equals 1 and -1. So this curve, this parabola will be have a higher curvature, look like this, still have -1 and 1 there. So it's had the net effect of essentially expanding this curve in the y direction. Now, because I'm trying to do all this on one piece of paper here, I'm not going to be drawing all of these graphs to the same scale, so I apologise for that. You'll have to sort of think a bit more about what I mean when I say scaling in the y direction, but I hope it's clear from this graph. Okay, and in the second example then, we're going to be shifting by a value a, which is 1, so we have y equals f of x plus 1, and we're looking at this example of the parabola. And now we can see that from this graph, shifting up by 1, well actually this turning point now will be at the origin, and what were the roots cutting through -1 and 1 are now just shifted up. So this whole parabola is just sitting on the x-axis, and those positions formerly which were roots, -1 and 1, will now actually be coordinates sitting at y equals 1. You can see here that I'm trying to avoid writing the equations down, because obviously when we apply these transformations to f of x, what we could do is just multiply this explicit function by 2 or add 1 and just plot the new function that we see, but I'm trying to infer these from the actual sketch, because often in exam questions they may give you a shape of a curve without actually explicitly giving you a functional form, and you need to sort of use information from the curve to draw these transformations. So that's why I'm not really manipulating this expression explicitly. Right, okay, let's change colour for a bit of variety here as we do these x transformations now. So we're going to look at y equals f of 2x. And this starts to remind us of the whole f of apple business that I talked about in recent tutorial on functions. So naively you think, right, we're just going to expand by a factor of 2 in the x direction, but that's not actually the case. And the key to understanding this is to say, well, for this function, if you feed it the value 1, then it's going to return the value 0. So if we're plotting it as a function of 2x, then the roots of this curve will occur when x has a value such that the function sees 1 or negative 1, and then it will return 0. So that will actually occur when x is a half or negative a half. That's where the roots are going to lie. Because then, because we're plotting f of 2x, multiplying x by 2 will make these values 1 or negative 1. And then, because this function wants to return 0 when it has an input of 1 or negative 1, that's where the roots will occur. The value of y at x equals 0 is untouched because twice 0 is 0 and f of 0 still returns negative 1. Okay. So our curve will have still obviously be a parabola, but now you see that despite there being a function of 2x, it's actually been compressed. Right, very good. Now let's see, number 3, number 4, now we're going to shift. We're looking at y equals f of, and we're shifting by a equals 1, x plus 1. And again, we have to think about this sort of f of apple. Going back to our original function, so this original graph of y equals f of x is really a picture of the machine. So explicitly this x coordinate is the input to the function. So this tells us how the function or how the machine works. And what we learn from here, for example, is that if the function has an input of 1, it will return the value 0. If we're plotting f of x plus 1, we have to say, well, what value of x will be such that the function sees the value 1, because I know then it will return a value 0, and that will actually be x equals 0. So plotting this function, when x is 0, the function sees 1, and then the function will return 0, because from our original graph of the machine, as it were, we see that if it sees 1, it returns 0. So there'll be a root there. Similarly, if we choose x equals negative 2 here, the function will be of a value negative 1, and our original sketch of f of x says that if the function is given negative 1, it will return 0. So the other root is going to be at negative 2. So I feel I've made a bit of a meal of this explanation. I apologize. Sometimes too many words are unhelpful. But I am trying to get over this counterintuitive notion that naively one wants to shift the curve to the right. But by looking at a few points and explicitly thinking about the f of apple sort of metaphor, we see, in fact, the curve is shifted to the left. So one final point here then. With the original function, if it's fed x equals 0, it will return y is negative 1. Plotting f of x plus 1, if we choose x as negative 1, we're effectively giving the function the value 0 as an argument. It will return negative 1. So at x equals negative 1, we have y is negative 1. And that's going to be our parabola there. Okay. So the curve has been shifted to the left by a value 1. Had we plotted the function y equals f of x minus 1, the curve would be shifted to the right. Good, okay, and then finally we have the reflections, which actually will be a lot more straightforward. It's really these two involving x that are the tricky ones, which is why I've kind of got into them in quite a lot of detail, perhaps too much detail. Right, this y is negative f of x is literally multiplying every value of y by negative 1. We're reflecting the curve in about the x-axis, so that's really quite straightforward to visualize. Yes, got to refer to the right function here. Is this one? Okay, so this turning point at negative 1 will now be sitting at 1, and this valley-shaped parabola will be turned into a hill-shaped parabola. There we are, and these roots remain the same because the values where y is 0 will be untouched by this transformation. So right, I'll just write that here. So this is y equals negative f of x. And then finally, we have this reflection in x. And in fact, for the particular function I've chosen, nothing's going to happen, which is maybe a salutary lesson that sometimes the transformation will leave the graph unchanged if the graph or function has an implicit symmetry which is related to that transformation. So here then we're looking at y equals f of negative x, and you see because the function is symmetric already about the y-axis, taking this curve and reflecting it and taking this curve and reflecting it just leaves us with exactly the same function. And we just have that same parabola there. There's a good lesson to be learned here actually, which is regarding this last transformation of f of negative x. We do have a little bit of language which maybe I'll just put in a box here, be useful to know. And this relates to this transformation here, that let me write it in black. We will have functions, so if f of negative x is equal to f of x, we call such functions even functions. And relatedly, if we have a function such that f of negative x is equal to negative f of x, we call such functions odd functions. So I'm just mentioning that here because I will draw attention to this in future tutorials. This particular example we chose, this parabola negative 1 plus x squared, is an even function of x. One can see that explicitly if we explicitly write negative x. You see, by squaring it we have exactly the same functional form there, so that obviously the graph will not change. This is a very useful sort of set of properties to know about and to get used to trying to identify. So for example, straight line functions are odd functions. Parabolas will be even functions if they do not have a term in x. If they have a term in x, they will have no particular symmetry in this x direction. The sine function is an odd function. The cosine function is an even function. So we've actually been already dealing with functions which have these symmetries, but we've never really pointed them out in this formal way of even and odd. So I'll try to remember to do that in future tutorials. Right, thank you. I hope that was helpful, just listing these transformations and using this parabola as an example. Just to say again, the two tricky ones are really the scaling in x and shifting in x. They are counterintuitive at first glance. If you get more experience, they'll be more intuitive. But I think it's worthwhile spending time showing explicitly why one gets the form of functions from these transformations, to show that having a scaling parameter greater than 1 applied to x actually compresses the function, and having, say, a shifting parameter that is positive added to x shifts the function to the left. Right, thank you so much for your attention, and we are now about to embark on such a great adventure in maths, which is calculus. So I'm really looking forward to seeing you for those tutorials. So I'll see you then.